Let's go back to the definition of work done by a particle that goes from point P1 to point P2. To calculate the work, we need to integrate from P1 to P2 the force times dx. For simplicity, I will work in just one dimension. Inside the integral, I can substitute the force by m times a, and a as the derivative of the velocity with respect to time. From the definition of the velocity as well as the derivative of x with respect to time, I can also substitute dx by v dt. The integral, therefore, can be written as the integral of m times v dv because now my integration variable is the velocity. The limits of integration go from initial velocity v1 to the final velocity v2. I can now solve this integral and I get that it is 1/2 of mv squared, evaluated between v1 and v2. This 1/2 of mv squared is what we call kinetic energy. It is the energy that an object has due to its velocity. The more velocity one object has, the more work it can do. Also, the larger the mass, the larger the energy, and the larger the work it can do. We can write this result as the work is equal to the change in kinetic energy. This is the work-energy theorem. If the work is positive, then the kinetic energy increases in the process of going from P1 to P2. If the work is negative, then the kinetic energy decreases in the process of going from P1 to P2. Now, let's assume that there is an object going from a lower height y1 to a higher height y2. Because this happens near the surface of the Earth, there is the force of gravity acting on the object. I can calculate the work done by gravity on the object when going from y1 to y2. The force in this case is constant. The force is negative mg, so the work in this case is equal to negative mgh. Now, because of the work-energy theorem, we know that this work is equal to the change in kinetic energy. Kinetic energy at 2 minus kinetic energy at 1. Here the masses cancel and I can write the final height as the function of the initial and final velocities. If I want to know what is the maximum height of an object that an object can reach, I impose that the final velocity is 0 and I get this expression for the maximum height. H is equal to the initial velocity squared divided by 2 times g. This result we already found by kinematics calculations. Now we have found it using only energy and work. Let us now consider the following example. Assume that we have a roller coaster with a circular loop. The rails are frictionless. We want to know at what minimum height the car needs to be placed to go over the whole loop. Initially, the car has 0 velocity. The car needs velocity at point B of the loop. The larger the initial height, the larger the velocity at B. But because there is going to be a centripetal acceleration at the top of the loop, we better draw the free body diagram. The only force acting is the weight due to gravity. This force pointing to the center is equal to the centripetal force. From the expression for the centripetal acceleration, we can get the speed at b. Now we can use the work-energy theorem that says that the work done is equal to the change in kinetic energy. We calculate the work from the initial height y sub a to the final height y sub b. This is equal to the final kinetic energy minus the initial kinetic energy, which is 0, as initial car height and velocity. We simplify this and we get that the initial height is equal to the final height plus 1/2 of the radius of the loop. This is simplified by this. So only considering work and energy, again, we can find the initial height required for this motion to happen.